Hi, thanks for joining us today at Carmel Academy. I'm Dr. Courtney, and before we dig into today's experiment on the simple harmonic oscillator, let's talk about an important Bible. Let's talk about Hebrews 12:14, which says, "Make every effort to live at peace with all men and to be holy, because without holiness no one will see the Lord." And so let's talk about the making every effort to be at peace with all men, because in our efforts to do science like a boss, we need to clarify an issue. And that is, we know that in Genesis chapters 1 and 2, and it's also reflected in Genesis 9 and Psalm 8, God has appointed man as ruler over creation. We have authority over the fish of the sea, the birds of the air, the beasts of the field. We have authority granted by God over the created world. But what don't we have authority over? What are we not given to be boss over? And one of those things is other men. And when we're doing science like a boss, we need to take care that it's with the proper approach in our heart to exercise our God-given authority, and not to extend that or try and exercise authority God hasn't given us over other men. Lots of times science has been pursued to make lots of money, and we know that the love of money is the root of all kinds of evil. It's been applied to develop weapons of war so we can go take over the countries around us and exert authority over other men, and this isn't right. We want to make every effort to live at peace with all men, insofar as it depends on us, and to be holy, because without holiness no one will see the Lord. Okay, so the simple harmonic oscillator is simply a mass on a spring, bobbing up and down. And this isn't a physical system that occurs often in nature. However, there are many physical systems in nature that are approximated by the simple harmonic oscillator, that are well approximated by the simple harmonic oscillator. So if we can come to understand the simple harmonic oscillator and master it, we have a building block to understand lots of more complicated physical systems. Okay, the hypothesis for this experiment is that a mass on a spring oscillates with a period t given by t equals 2 pi times the square root of m over k, where m is the mass and k is the spring constant. And it's important both for your understanding as well as to execute this experiment that you have performed the earlier experiment on Hooke's law that really helps understand what this spring constant is. And if you recall, the spring constant is the slope of the line when you plot force versus displacement of a spring. And we measured that very accurately, and hopefully you measured that very accurately in your experiment on Hooke's law. Units are important. We want to measure the mass in kilograms and the spring constant in newtons per meter. And if we take care of our units, then this formula will predict the period of the simple harmonic oscillator in units of seconds. Okay, so our strategy for this laboratory is to predict the period t, and the period t is the time it takes to make one complete oscillation. And for the purposes of this lab, we're measuring it from the bottom-most position of the mass, bounces up and comes back to the bottom. So the time between being exactly at the bottom once and being exactly at the bottom again is the definition of the period for our simple harmonic oscillator. So we're going to predict it with the above formula, but to exercise that formula we need an accurate mass determination. So an electronic balance can be used if you don't have calibrated masses where you already know the mass very accurately. And the spring constant needs to have been measured in the Hooke's law experiment. Okay, so we're going to predict the period with the above formula, and then we measure the period using the video camera and tracker. And the strategy here is to time it for 10 periods, bouncing up and down 10 times, because this gives us a little more accurately, and then we're simply going to divide 10t by 10 to give the period of a single oscillation. And then we're going to compare our measured period with our predicted period, and that allows us a test of the hypothesis. Okay, so this is our first video file for the 100 gram mass. We've imported it into Tracker, and notice that we have zoomed in so that we can see the motion of the bob bouncing up and down pretty well, but we don't need lots of other stuff in the room or the experimental apparatus, so that was our level of zoom. So now we move forward frame by frame, and we just want to catch the mass at its minimum point at the bottom of its bounce. And there it is right there in frame 12. So once we get, this is the 0th bounce, we're going to count forward for here, and we're going to set the time to 0 corresponding to this first lowest point, and then we're going to let it play through, and we want to get the 10th bounce. So that's the first bounce. That's the second. That's the third. That's the fourth. That's the fifth. That's the sixth. That's the seventh. That's the eighth. That's the ninth. And now we're gonna slow down a little bit because we want to make sure we get it on the 10th. So that's the 10th bounce. So that number there, 4.638, is the number that we write in our lab notebook for the 10T corresponding to the 100 gram mass. Now in the actual experiment, we're recommending that you use 3 or 4 different masses. I got some commentary back on the video analysis that we don't need to show the level of analysis for every data point. So we're going to skip forward, even though off screen we analyzed it for 200 gram and 300 gram. We're going to skip showing those and go to the 400 gram mass. And once again we step forward to the first minimum. Which is this point here, the 27th frame. And now let's go ahead and set this time to 0. And now we're going to go through 10 periods, 10 bounces, and that'll help us determine what the 10 periods are, and then we'll just, in our analysis phase, we'll go ahead and divide that by 10 to get 1 period. Now it's important to count these bounces carefully. One of the most obvious mistakes comes from miscounting the bounces. So you want to make sure you start with 0 and it's your first bounce, and count to 10 carefully that way. Alright, that's 9. And that's 10 right there. Okay, so that's the 10th bounce. So the time, 10T, is 9.209. So we write that in our lab notebook. And we'll go ahead and show you our completed lab notebook for all 4 of the masses. And we happen to have these handy dandy calibrated masses and nice even units of 100 grams. If you used different masses, as was kind of explained in the Hooke's Law video, you'll need to go ahead and weigh your masses and determine those accurately on your electronic balance. Okay, so this is our analysis spreadsheet, where all we've done so far is we've set up our columns. Well, we entered our spring constant here because we'll need it to compute our predicted periods. And we set up our columns, mass in grams, our measurement 10T, and we just copied our lab notebook exactly into those 2 columns. And now there's some computations need to happen in the 4 rightmost columns, so let's walk through that. The spreadsheet formula wants the mass in kilograms. So we go ahead and highlight this element here, and to compute that, it's just the mass in grams, which is A5, and then we divide by 1,000. Okay, and we know that makes sense. 100 grams is 0.1 kilograms. And then we copy that formula and we go ahead and paste it down for the rest of that column to get the mass, all of our masses in kilograms. Now our measured period here is just going to be this element B5, and then divided by 10. So we type in the formula B5 divided by 10, and now we can go ahead and copy that and just paste that down for the rest of the row, and this would be our measured period for a single bounce. It's just 10 bounces divided by 10. Alright, now a little more effort is required for our predicted period T, and this is where we test our hypothesis. So this is equal to 2 times pi. You probably don't need all those digits for pi, but I'd have maybe at least 5 significant digits, and then times the square root of the mass, but we want the mass in kilograms, so here it's element C5 divided by the spring constant K, and the spring constant K is an element D1, but we use the dollar signs here, $D, $1, so that when we cut and paste that formula down, it will still be referring to this element and not the columns or the rows below it. Okay, so go ahead and copy and paste the formula for the predicted periods down. And so now we have our 4 measured periods and our 4 predicted periods corresponding to each of our 4 masses. And now we can compute the relative error. And if you recall, the relative error formula is our prediction E5 minus our measured, which is D5, divided by our measured, which is D5. So this is a nice result. Our relative error, at least for that data point, is 0.0011, or it would be 0.11%, or approximately a part in 1,000. And that's kind of a happy accident. We don't really expect our relative errors to be that good for every data point, because keep in mind our accuracy in measuring the period is about 1/300th of a second, or about 30 milliseconds, because our accuracy for measuring 10 periods is 1 frame in the video camera, which is about 1/30th of a second. So we can see that when we compute our other relative errors, they're all under 1%, but some of them, this is about 0.9%, and this one's about 0.8%. So our hypothesis is supported with a nice level of accuracy. We find what I would call strong agreement between our predictions from our hypothesis and our measured values. Wow, that was a fun experiment. I always strive in my design of experiments and in my experimental care to have agreement between theory and experiment with an accuracy of 1% if I know that the theory should be well supported, and this is a well-established result. So if your accuracy is a whole lot worse, like 5% or 10%, I hope you give some care and consideration to what you could do differently on your next experiment to improve your accuracy. Thanks for joining us today at Carmel Academy. I'm Dr. Courtney.